So we are all aware that this is towards the AWS AI practitioner exam,
Yeah.
right?
Yes.
Okay. And the second phase, what we are focusing on is deep learning, which is
Yeah,
um
Mr. Chichi.
hello?
Okay. That's my that's it. I'm sure. Okay.
We're focusing on deep learning, which is a subfield under machine learning, right? And I understand that you went through basics in machine learning in the previous phase, right?
Hello, madam. I didn't speak. Oh,
Oh, I think you were off when I called. Can you
oh,
introduce
sorry.
yourself?
Please, my name is Joyce, and I am a nurse. I'm into nursing. This is my first time doing something different. I want to like break into IT. I want to
Oh,
try
okay.
something new.
That's great. Thank you.
Thank you too.
Okay. There's also Yao. Yao, can you hear me?
Hello, please. Hello,
Yes, hello.
please. I didn't hear what you said.
I wasn't calling you. I was calling someone
Okay.
else.
Oh, sorry.
That's okay. Yao, can you hear
Hello.
me? Hello.
This is Yao.
Yes.
Yeah, this is my second course with Get Skills. So I'm a bit new to the AI practitioner, but I was in the previous course, willing to catch up uh, pretty soon.
What did you
Thank
study
you.
in? What did you study in the university? Or what field are you currently in?
Um, Architecture,
Architecture.
engineering. Yeah.
Do
But
you
I'm just
have
trying something new with cybersecurity as well. So I was just wanted this one to that.
okay. Do you have any background in coding?
Just a little bit, just a bit of Java, C
Okay.
plus C plus plus. Yeah.
Okay. Yeah, that's fine. So
Thank you.
thank you. That's great. So let me first of all start sharing my screen. Kindly confirm that you can see my screen. Okay. Yeah. So as I was stating before, this is the deep learning side of things towards the same exam. And we have 4 to 5 sessions to cover um concepts and some practicals on deep learning and different architectures that fall under deep learning. Okay. So um before I start, I want to have an idea because I know you've already started with machine learning. You already done some basics. So I would want to know just what you understand. Okay, so what I'm going to do is Mhm. I'm going to do is to ask you some 1 or 2 questions. Who can tell me what machine learning is? In your own words, it doesn't have to be an exact explanation. Anyone? You can also type in the chat, you don't have to speak out.
And please let me try.
Hello, yes, you can speak.
We said that machine learning, in my own understanding, is giving taxes to computers, like so that they can make ways human beings do their things.
Can you come again?
I said that machine learning is that you are getting you are giving computers tasks, and then they will have to mimic humans.
Okay, thank you. Is there any other thoughts? Okay. Daddy
Yes,
says training machines to think and act like humans. Okay. Anyone else? John?
yes,
Okay.
Yes, what do you
How
think?
It
machine
is
learning?
the training of machine learning algorithms with data so
Mm-hmm.
they can make decisions on their own. Training
Okay.
of machine learning algorithms with data
Hmm.
so they can make decisions on their own.
Okay. Thanks. Thank you for that. So that's a good that's a good thing. So everything that you said um is some way somehow related to machine learning. I'm yet to hear like some very specific things I was hoping to hear. Does anyone else want to give it a go?
yes, please.
Yes.
I, to my understanding, I think machine learning is feeding computers with data and giving them patterns to work on so that they can solve real-time problems.
Okay. Giving them patterns. So there's definitely patterns in there. Um, but in this case, usually for machine learning, you're not giving them the patterns, rather you are giving them the opportunity to identify the patterns themselves. So someone mentioned training machines to think and act like humans do. Interestingly, that is a very good description, not of machine learning, but of AI, which is the broader term. So there's AI, and then there are different subfields under AI, under which machine learning is found. So AI is artificial intelligence, and you can think of that as being able to give or maybe giving the machine the ability to do what human beings can do. Then under AI, um, we have subfields like computer vision. I don't know if you've heard of computer vision before, CV. Computer vision is giving the machine the ability to see or see and then interpret what it sees, like the way human beings do. So it's image processing, videos, etc. Then we have NLP, natural language processing, which is giving the machine the ability to communicate in natural language or communicate the way human beings communicate, and then understand and reason the way human beings do. Then we have machine learning, another subfield, which is giving the machine the ability to learn in the way human beings do. How do human beings learn? They learn from experience, right? We learn by observing different instances and then drawing patterns, drawing connections ourselves. So machine learning is a subfield of AI, all towards getting the machine to act like the way human beings do, but then it's focused on mimicking the way human beings learn. Do you understand? Do you understand? Okay, great. Okay, so I know that you went through some uh machine learning algorithms. What are some examples of algorithms that you've met from the previous session? You can speak or you can type.
Linear regression.
Linear regression. Uh-huh. Did you learn any other one? Classification is one of the types of machine learning problems. Um, but it's not an algorithm. Okay, there's decision trees and random forest. Yeah, there's. Wait, Patrick. Patrick, you didn't introduce yourself.
Sorry about that. I went to the washroom.
Okay.
Yeah, my name is Patrick. I currently looking to break into cyber. I was working with cyber, but was looking to look more into like AI stuff. I went to school for IT, and that's about me.
So you studied IT?
Yes.
Okay. So you know how to code?
No.
No. Okay. That's fine. All right. So that's just we are going into the course, don't worry. I'm just getting you from what you know, um, to what you don't know. So we have linear regression, decision trees, random forest. Does anyone know any other machine learning algorithm that exists? Is this all you covered in the previous phase?
Logistic regression.
Okay, logistic regression. Okay, any other? One more. One more. Vector machine, support vector machine, yeah. SVMs. That's good. So these are examples of machine learning algorithms. And the way machine learning algorithms work is that they take in a lot of data, identify patterns in the data, and use that to make predictions or make decisions on new unseen data. Okay. What we are going to be doing over for this session, um, is to first of all, okay, so what we're going to do is to understand what deep learning is, why it exists, and how it's different from classical machine learning. So classical machine learning is what you have done before, is what we've been discussing. Okay. We'll look at the basic building blocks of deep learning. Okay. So there are the neurons, layers. We'll look at the neural network as a whole, what they are in plain English. And then we'll look at how neural network make predictions and make and correct themselves. Okay. So when we say make predictions and correct themselves, that's the process of training. Okay. You've come across training of machine learning methods. So deep learning also has um, a similar training concept. Okay. Then we'll look at overfitting and underfitting. And then some other key terms within deep learning, like batch and real-time inferencing. And then we'll get to the coding part where we'll be able to build a three-layer neural network. Now, I know that we have a catch-up session for 1 hour during the week. So I'll try my best to be done by 9, but if we are not, then we will do the practical session during the catch-up. Okay. Is there any question up to this point? So deep learning is a subfield of machine learning. So it has the same use or the same importance or the same aim of being able to train the computer or train the machine to learn the way human beings learn, but then it just does it in a different way. So we'll actually look at what distinguishes um, deep learning from classical machine learning. Okay, we'll look at that in due time. Hello? Sorry, my internet's dropped off. Um, Kindly confirm you can see my screen. Okay.
Please, I think there's a glitch in the internet at her side, so let's just be patient more. She'll be back with us.
Okay.
Okay.
Yeah. Mm. Okay. I'm having issues with my Wi-Fi. I'm so sorry about this. Just give me a moment to bring this here. Bring that here. Okay. So, what we are going to look at first is what distinguishes classical machine learning from deep learning. Okay. So, with classical machine learning, from what I believe you've covered in the previous session, you give the model data, which is usually in a tabular form, right? I know there was this example that you used in one of the sessions you did that had to do with predicting the price of houses. Am I right? Using data on things like the house size, number of rooms, etc. Am I right? You did something like that.
Yes.
You did. Okay, good. So one thing about classical machine learning um, tasks or use cases is that usually you are going to work with tabular data. Okay. So where you have the rows representing the records and the columns representing the features. And you usually have a label. So the label might either be a continuous variable, continuous meaning that the values can be numbers within a particular range or that are not discrete, in which case you are working with um, a regression problem. Or it might be discrete or categorical, in which case you're working with a classification problem. Okay. So with classical ML, this is how it usually is. You have features with labels, and this is usually in a tabular or structured form. The other thing about classical machine learning is that when the model learns from the data, what it's learning is a rule that maps features to labels. Some examples are regression and then classification. Some examples of ML, classical ML problems or use cases are regression and then classification and then clustering. Okay. Regression and classification fall under supervised learning. Clustering falls under unsupervised learning. I believe this is something you already know. Okay. And then some examples of the classical machine learning models. There's decision trees, there's random forests, there's SVMs. Scikit-learn is just it's a library in Python that usually implements classical machine learning with.
Hi, Chantelle. Sorry to draw you back. Just a quick one. So when you asked about the types of algorithm, you just mentioned classification and then linear under supervised learning. So does it mean that then the algorithm is supervised learning and not the linear regression? I think that bit of clarity, if you can.
Okay, so when we talk about classical machine learning algorithms, we don't talk about regression and classification. There's a difference between regression and linear regression. Okay, so if we talk about classical machine learning, okay, there's supervised, unsupervised. Then under supervised, we have regression and classification. These are the kind of problems you might have. And I mentioned that a regression problem is a problem where your label is continuous. And a classification problem is a problem where your label is either discrete or categorical. Now, under these two, under regression, we then have examples of machine learning algorithms that solve regression problems or that model regression problems. Then we can have linear regression, you can have KNNs, you can have what again? There are so many different ones. And then under classification, we can have SVM, we can have random forest can also be used for both regression and classification, decision trees similarly, etc. Okay, so regression and classification itself is not an algorithm. It's a kind of problem. And depending on which one it is, there are algorithms that um, are able to be used to solve that kind of problem. Do you understand?
Yes, yes. I think you've done justice to it. Thank you.
Okay, welcome. Great. So one thing that you will notice with tabular data or with the kind of data that usually used for classical machine learning problems is that um, in these tables, every row represents an independent record, what you see in row one has no direct bearing on what is there in row two. Okay, the data is very structured in that way. So what happens when you have data which doesn't necessarily follow this pattern? For example, time series data. Okay, data where maybe it is weather. So with the weather data, each row might represent maybe a point in time, maybe a dates, different dates or different hours in a day, different years, etc. In that case, it's not structured in the normal way we know. And classical ML generally breaks down for data that isn't in that kind of structured way. Okay, so whenever something like maybe the rows no longer are independent, or it is not even in tabular form anymore, it is like maybe text data, like maybe Wikipedia articles, or we have image data, like several images of cats and dogs and things like that. One might be able to try and structure it. Um, it will take a lot, and then you might lose some information by restructuring the data, especially when it comes to image data. So deep learning is that subfield under classical machine learning that tackles um, data that is unstructured. Okay. Deep learning itself is quite broad, and there are so many different models that are under it. And usually they all each type of model handles a particular kind of data. Okay. I hope I'm not being too technical. If at any point I'm being too fast or what I'm saying is flying over your head, please draw me back and then ask me to clarify. Okay.
I have a question.
Okay.
So, machine learning, we said that it tackles the tabular data, and then
Mhm.
for deep learning, that tackles unstructured data. Is that correct?
Yeah. Classical machine learning. So deep learning is under machine learning, but we have classical and then deep learning. Do you understand?
Hmm. So then, example for deep learning would be, I guess, unstructured data could be like music files,
Mm-hmm.
um, different types of files like Word documents, pictures that are like maybe like stored in a storage like an S3 bucket or something like that. Is that
Exactly.
correct?
Yeah, exactly. Exactly. So let's take, for example, a phone that is able to do facial recognition. Okay. The um or yeah, let's say facial recognition. Okay. It's able to first of all, it's you have to configure it, right? So with configuring it, you show it to your face, maybe you move a bit, and then it has registered your face. And later on you can come and then it's able to recognize your face, right? Now, when you think of a camera and the way a camera works, a camera just captures images, right? When the images are stored in your gallery, unless there's some AI tool in there, your gallery doesn't have knowledge of what the picture it has taken is. It only stores it, right? Now, the ability to, or let's say when we are able to give the machine the phone or an app, the ability to understand what it has seen, that okay, this is a person, or this is the owner of the phone. This is a cat, this is a dog. When it's able to make an interpretation of the date of the image that it has seen, then there has been some learning that has taken place. And that's what computer vision is really all about. Okay. So it's about giving the machine the ability to interpret and understand what an image actually is saying or what the image actually is, and not just storing it. Okay, I'm going out of what we are discussing, but okay, so that's that. So in summary, classical ML is usually working with structured data and deep learning unstructured data, and that's what we're looking at in this phase. Now, classical ML is very important. It has its place, and there are things that it does really well at. But to motivate deep learning, we'll look at where classical ML breaks down. Okay. Um, yeah, where classical ML breaks down, let's just leave it at that. So, classical machine learning. Hello? Hello? So in the last session where I heard you guys working on um that housing data, what did you guys do? The first thing you did was to explore the data, right? And you were supposed to also clean the data, right? So explain the data to just see basic patterns, clean the data to remove um any irregularities that might affect your model. Okay. Another step usually in the classical ML process is feature engineering, okay, or feature selection. So usually, I don't know if you've heard about this, but there's something that is commonly said in machine learning that garbage in, garbage out, right? So if you give a model data which is nonsense, you're going to get a nonsense model, right? Because it's learning based on what you give it. And because of that, classical ML and the accuracy or how well classical ML models do is really based on how well you are able to select the right features to train the model with. Okay, so there's a feature engineering problem. So with classical ML, human beings need to define what features or what are the best features to use to train a model. Taking into consideration the fact that if you give it features that um, are not as relevant, the model might learn useless things or might identify patterns that don't exist or things like that. So classical ML needs humans to define what matters. If we considered an image recognition task, to recognize a cat, you would need to manually describe what the cat's fur looks like, what the cat's ears and whiskers look like in numbers, and for all possible variations. Now that's not possible because there are so many possible configurations and variations that come with something like that. So that's one place where the classical ML breaks down. Now with deep learning, um, feature selection and feature engineering is baked into the algorithm. You don't need to do it. Okay, so that's one thing. Classical ML breaks down, as I said, with unstructured data like images, speech, text, video. And these are the reasons, right? So with images, there are millions of pixels. So with images, a digital image is basically just numbers, right? The pixels represent numbers. So ideally, as I mentioned, you can regularize it and um make it look structured. However, just the fact that it's an image, and images usually have lots of pixels, that makes the data really, really large. And another shortfall of classical ML models is that when you have too many features, there's something called the curse of dimensionality. So it kind of means that the model cannot do as well. Okay, but deep learning models are much better at dealing with such situations. Okay, so for images, speech, text, classical ML breaks down with this kind of data. This one here shows the difference between classical models and deep learning models with increased amounts of training examples. Okay, so Well, let me make sure you're seeing. Yeah. While more data usually means that the model gets better, for classical ML models, there's always a point where they plateau. They get good until the point where they cannot get better anymore. And that point is usually below that point for deep learning models. Okay. And this plateau is because of so many different reasons. Okay, that we will not have to go into. But then it tells just this graph is just telling us that for deep learning models, they do way or significantly better with more data. While for classical ML models, while they will improve with more data, they will plateau at a point. Okay, at a point below deep learning models would. So classical ML requires a human expert to pre-digest the data, and deep learning usually just gets better with more data. Okay. So as I mentioned earlier, the limitation is the case of dimensionality. You can read about them. Okay. Which says that as the number of features grows, classical algorithms need exponentially more data. But deep learning sidesteps this by learning hierarchical representations. We'll not go too deeply into that. Okay. Any questions so far?
Yeah, I have one question.
Okay.
It's just for the classical, right? So for classical, how do you ensure that you've selected the right features?
Um. So the thing. So I mean, first of all, there's exploratory data analysis to help you to identify um possible obvious relationships, right? And then domain understanding helps to know what are some of the features that are going to be relevant. Okay, so for example, uh what's it called? There was this data that did I created a model for, and it was related to cardiac arrhythmia. Okay. So the data had several columns, which were like, they were the heart rate related metrics. And I didn't understand the metrics. But once a medical student picked it, they were like, okay, this and this and this are going to be more important in identifying whether the person has the arrhythmia or not. Right? So having domain knowledge also helps in being able to identify which which features are important. Otherwise, what you can also do is to try out different features, different combinations, and then observe how well they do in the prediction. So it's really an experimentation thing. Okay. And there are different methods that you can use to um, identify which features appear to be doing better at predicting certain things. I don't know if I have answered the question or I've confused you.
Yeah, so I guess the thing is that I guess from a classical ML perspective, is it possible that the output or the information that's being provided would be invalid, and you as the data scientist, you wouldn't necessarily know if you don't have the domain knowledge. Does that make sense?
Um, are you saying that um,
So
there's a
so using
possibility
your
that you might
example,
have data which is totally irrelevant to the kind of thing you're trying to do, and
yeah,
you will not
yeah,
know
so
because you don't have domain knowledge?
yeah, so for your example, you said you did something for heart arrhythmia, right?
Mhm.
So what was the problem you were trying to solve there?
So the data I had was basically the readings, or let's say vitals information had been taken of several patients that had come to the hospital,
Mm,
and the labels were whether they had one kind of arrhythmia or another, or they didn't have arrhythmia at all. So we're
mhm,
trying to create a model that takes in patients' vital information and then predicts whether they have arrhythmia or not, or what kind of arrhythmia they had.
mhm.
So some vital information was more important and others were not relevant at all. For example, the gender wasn't relevant.
Mhm.
However, maybe the maybe the width of a particular P wave or something was more important. Do you understand?
Mhm. So the outcome is to determine if the patient is, I guess, susceptible to a heart attack. Is that what you were
Yeah,
trying to solve
basically.
for?
Yeah, yeah.
Okay, so then if you don't know what if you don't have the domain knowledge and someone isn't there to provide the domain knowledge, and you start selecting features that you think based off of trial and error would be relevant, um, it is possible that the output that the model will provide you may not be accurate from uh, a health perspective. Does that make sense?
Yeah, yeah, it is possible. And actually, while like without the domain understanding, um, you are at a disadvantage at choosing these some of I mean, the best features. The importance of EDA is to help you to quickly identify those that have no correlation. So, for example, um, gender. If I had the data and half of them were females, half of them were males. Okay. And I did EDA, maybe I do some kind of bar plot. And the bar plot told me that, or let me say, no, maybe not say bar plot, let me say, um, maybe a pair plot diagram. I don't know if you guys have done that, but something that's able to help you to picture, um, of all the patients, how many females had it, how many females didn't have it, or how many females had it, how many males have it. Okay. And then if we did something like that, that's at the EDA step before you actually go to ML. If you did something like that and you saw that, okay, out of all the females, maybe 80% had it, and out of all the males, maybe 20% of the males had it, then um, it might lead you to be a little curious as to whether there's a relationship between um, the gender and then having it. Not to say that that is a conclusive thing, because correlation doesn't mean causation. But at the EDA step, you might get some hints on some things that might be interesting to look more into, or some things that obviously have no bearing at all. Okay. So you might observe those things, and then if you get a chance to talk to a domain expert, they may or may not confirm it based on the data, based on the domain knowledge, and what is in the data. Oh, I think we're off track. Let's go back on. Um, but I hope you're okay, Patrick. Okay, great. So as I mentioned earlier, AI um is the superset, and then we have machine learning, and within machine learning we have deep learning. Okay. Now let's go into the basic building blocks of deep learning. Deep learning is I mean, the main architecture, okay, that builds deep learning is called a neural network. Has anyone heard of a neural network before? Has anyone heard of a neural network? You can type in the chat. Oh, you learned it in the first week. Okay, so you know about neurons. Okay, you didn't go into it. All right. So neural networks are kind of algorithm which mimic the the way the brain works. Okay. So you know that in the brain you have neurons, right? Um, let me do this. Let me show you a comparison between neural networks in the brain. Okay. So this is what a neural network looks like, the one on the right. Okay, so these circles, can you see? Yeah. These circles here are what we call the neurons. Um, you can compare them to this portion here. And then the lines here are called weights. Okay, and you can compare them to the dendrites here. The dendrites are responsible for passing information between one neuron and the other. So the weights are also some kind of quantifier, okay, um, between one neuron and another. Okay, so and I don't know if you know about the way in which we learn things um, from the idea of the neuron. So the more you repeat certain things, whether it's if you are doing words learning, you are repeating words, or whether you are repeating certain habits, there are neural connections being formed. And the more you repeat it, the stronger the connections. And they become strong enough you don't forget long-term memory. Similarly, when you train, the weights, which are the connections between the neurons in the neural network, are set. Okay. So as you train, they are going to be set and reconfigured until they get to a point where the values have the values that are set define some pattern um that has been learned from the data. Okay. So I'm trying to just give you an analogy between the two. Um, let's move on. This is a single neuron. Okay, so you can think of this one. Okay, let me share that. Let me split this. What did I do? Let me split this. Okay. So we have this, and then we have this. So you can look at this neuron diagram here as any one of these. Okay, so let's maybe consider this the second hidden neuron here. So it has these lines here, which I said are called weights. So they are weights and biases pointing to the neuron, and then there's an output. In this case, there are multiple outputs anyway. So this is the most basic block of um, a neural network, which is a single neuron. Okay. And as I mentioned, these are the weights. X1, X2, and X3 represent inputs from other neurons. Okay. So you can think of this place as having some other circles here representing neurons. So there's the inputs from the neurons. The weight represents um, the level of importance of the information that is getting from X1. Okay, so yeah, the W1 represents the level of importance that is being assigned to the input that's coming from X1. Same for this and same for that. A bias is just a constant that's added, and then the output is it's actually a simple mathematical calculation done between these values here, X1, W1, X2, W2, X3, W3, and then the B. That will give you the output. Okay, this is actually mathematics. Okay. So the single neuron does three things. Number one, it receives inputs. So the numbers come in. So for example, if we look at the price prediction for the house, you can think of the inputs here to be maybe one will be the house size, then the other one will be the number of rooms, the third one will be um maybe the number of schools in the area or something. Okay. And then it's multiplied by the weights, and then you add a bias, and then you apply an activation function. Okay, and that will give you the outputs. So that's all that you should know about the neuron. Okay. Any question at this point?
So please, does it mean the neural network is like it has been inspired by the human brain and then
Yes.
it's recognized like hidden patterns. So within time of practice, that's when it gets like its accuracy or at its infant stage of using it.
So at the very beginning, that when in the training process, the thing that is being set is the weight values, which is, as I mentioned, is the level of importance that is being given to the input um from the different um neurons that are coming, but different neurons giving information. Okay, so at the beginning of the training process, the weights are set randomly, and as the training process happens, the weights are um continually refined until they reach values where um, they give good results. Okay. I should explain the activation function. The activation function um, is the last piece of computation. So how do I show you this? I'm going to find an image to show you. Mhm. Very good image. Okay. Let's look at this image here. This one here. Okay. So this is mathematics, and I don't really want us to dwell too much on the math. Okay. So this is a neuron here. Okay. And as I told you, the weight is going to be multiplied by the inputs, and then you add the weight times the input of this, and then you add a bias value, which I said is a constant. Now, before you pass it to the next level, you have to um I won't say compose, but that's like a mathematical like compose. So whatever the value is, you apply a function to it. So that function applies the activation function. And the reason you apply an activation function is to prevent the values from exploding. Okay. If at any point your weight reaches a really large number, okay, let's say your weight reaches like 1,000 or 2,000, and this one reaches like another 1,000, your values can easily explode such that it will be hard to even um it will be hard for the model to capture any meaning. So the activation function is there to prevent that by always making sure that the values are within particular ranges. So some common activation functions that you will see as the sigmoid function. The sigmoid function keeps values between -1 and 1. Or is it 0 and 1? 0 and 1. Or the tanh is -1 and 1. So it's a mathematical thing really. And it just helps to prevent the numbers from exploding or from growing so big that the model is not able to learn. Okay. As I said, it's a mathematical thing. You would not actually need to know much about how it works because in coding, you don't really do this part. Okay, this is all handled by the deep learning library that you'll be using. Okay, so it's just for you to know. So we have the weights, they have the bias, they have the activation function. And they would basically determine how a neuron receives information and how it passes it on to the next neuron. Okay, are we all okay at this point? Okay, great. So this is similar to what I showed you before. In a neural network, or a very simple feed-forward neural network, this is how it looks like. The first layer you see is called the input layer. So the input layer is the layer where your data is found. So let's say, for example, you wanted to train a neural network to recognize images. Okay. Your image, as you know, a digital image is made up of pixels. Pixels are, you can think of them as numerical values. Okay, where each value represents a color. Okay. So in the input layer, if we are looking at it as pixels, the input layer would be the pixel values which have been stretched into one vector. Okay. That's what the input layer represents. The hidden layers here can be set by you. Okay. Or no, they must be set by you. Okay. So generally, the more neurons in the hidden layer and the more hidden layers you have, the more complexity your neural network is able to capture. Okay. However, the more neurons you have in the hidden layer and the more hidden layers you have, the longer and the more data it would take to train the model. So you always have to have that balance between having enough neurons in the hidden layer and layers of enough hidden layers to capture the complexity that you want, but at the same time, not to overdo it, such that you know, I mean, it's always better to have the simplest thing that can solve the problem than to have an overly complex thing that can do the same thing. Okay, so that's the hidden layer. That's what determines, or that's what captures the complexity or patterns in your data. And then the output layer is the final prediction of your neural network. Okay, so this is what gives you the final prediction. So let's look here. So the input layer is where the raw data enters. One node represents one feature. There's no computation happening at the input layer. It just receives information and then passes it forward into the hidden layers. Hidden layers are where the computations happen. Hidden layers. This is where all the learning happens. Okay. Every layer learns increasingly abstract features. And more layers means more complex patterns. Then we have the output layer. This is where the final prediction happens. For a regression problem, you use one node. And then for classification, it depends on the number of classes that you have. Okay. So what we'll do now, let's go to playground.tensorflow.org and just look at a neural network. So in this case, what we have here is the input layer. Have I lost anyone at this point? Are we all on track?
Please, the
You lost me.
input layer.
Yeah.
You said
The
it
input
only,
layer.
yeah, it does not need any computing or it does not do anything. It just receive the information, the raw form, and then pass it to the hidden form.
Yeah. The hidden layer.
But if it doesn't like analyze or categorize the information, where like how is it going to determine where to pass it through?
Um, when you say where to pass it through, what do you mean?
Like, so I'm asking if like it doesn't process the data or analyze it, how is it going to pass it to the next layer? Like to know which layer to pass it through or to pass it to. Like if the input layer doesn't process the data. Because in the slides you are showing, it says it does not need any computing process. You just take it raw and then the next thing is passing it to the hidden layer.
Okay, so I guess your explanation, your question is because I haven't really explained the way in which the training works. So the way in which training works is that, as I mentioned earlier, the input layer is is the point at which you are giving the data to the model. Okay. So let's say you give it to the model Should I do an example? Um, how will I even? Okay, let me see. Maybe I can go do a whiteboard or something.
I believe you should teach us how the information are being passed, the process that you're going through, so that we can get the more like the concept of it.
Yeah, yeah, I think so too. I think so too. So, um, what should I do now? Okay, let me stop sharing. Let me create a whiteboard. Okay, can you see? Okay. So let's assume that we want to create a neural network. Okay. And the neural network will take in the price of, or let's say it will take in house, some features of a house, and then predicts the price of the house, just like what you did with classical ML. Okay. So it's going to take in three features. It will take in, so let me see what we want to do. Problem. We want to create a neural network network that takes in, or that's, okay, that determines the price of a house given the, what should I even use? Given the number one, number of rooms, size of the house, and then um, number of
Maybe.
floors
Okay.
in the house. Okay. So in this case, it is, can someone tell me, is it a regression or classification problem?
This is a classification.
Why classification?
Okay, so you're dealing with price, so that's numbers.
Mm-hmm.
So that should be a regression, not classification,
Yeah,
because you're not looking at the different types of houses, you're looking at the numbers with regards to pricing.
exactly. Exactly. So, as I mentioned, it is regression when your label or the thing you're trying to predict or make a decision on is continuous as a continuous value. So it might even still be a number. But if it is discrete, let's say I want to take some input and then maybe predict the number of people in the house. Um, no, not number info. Okay, you can say number info, yeah. It can be looked at as a classification problem because you are dealing with discrete numbers and probably it's not going to be out to infinity. Probably you have maybe like 1 to 10 or something. So when you have a definite number of possible outcomes from your decision, then it's classification. But if it is something like price is continuous. You can have your price being 100, 100.1, 100.11, 100.123. It's continuous. It's over a range that has no limit. Then it's regression. Do you understand? So in this case, it's the price of the house. It's a continuous variable, so it's regression. Um, Our label is the price of the house, and then our features are number of rooms, size of the house, and number of floors in the house. Now, these are only three features. So it means in our input layer, how many neurons will we have? Any idea? Three. So the number of neurons depends on the number of features you have. If you are using an image, if you want to do an image classification model, um, if you want to do an image classification model, and your image is 360 pixels or 720 or 1080, whatever the number of pixels is what will be the number of neurons in your input layer. Okay. So if you had a 1080 pixel image, then you would have 1080 neurons in your input layer. Now we only have three, so we will just have three inputs. Then when it comes to the hidden layer, as I said, it is your prerogative to choose the number of neurons you want and also the number of hidden layers you want. And I said that the more the neurons and the more the hidden layers, the more complex the model you're building. The more data you will take to train it, and the more time you will need to train it. Okay, Patrick.
The question I have is, you said that in the hidden layer, it's up to us to choose the neurons. But
Yeah,
before
the
that,
number of neurons.
you asked us what would the number of neurons be in the input layer. So I'm a little confused.
So when it comes to the inputs and the output layer, the number of neurons you would choose
Is different.
doesn't depend on you. It depends on your data and your problem. So for input layer, is dependent on the number of features you have in your data.
Okay.
But the output layer depends on whether you're doing a regression or classification. For regression is one. You have one neuron in your output layer. For classification, it will be depend on the number of classes that you have. Okay, so the number of classes will be the number of neurons that you would have.
Okay, and then for the hidden layer, the number of neurons depends on what we decide. Is that
Yeah,
correct?
exactly.
Okay.
Okay, so for this example, I just want to show you how it works. So I'll just do three neurons, one hidden layer for the hidden. So this is input. Let me label it there. This is the input layer. We're actually moving ahead of the slides. You'll see this again later on. But anyway, let's go. So we have three neurons here in the hidden layer. Oh, and hey, what has happened? Who is that? Who is that? Can I undo?
So input layer and hidden layer number of neurons, they don't have to be the same though. It could be
No,
one,
they
it
don't.
could be
Yeah,
okay.
they don't have to be the same. Yeah.
How do you determine how much neurons to use in the hidden layer? Is it just
So
up to you?
yeah. So as a rule of thumb, you want to start with a smaller number and then increase it as it goes. Usually, you want to start with maybe um. I think usually they do 128. Some people do 64. There are some specific numbers that they choose. I don't really know why. But all I know is that perhaps it should be more than the number of inputs neurons you have. Maybe you can start with like two times of the number of inputs you have.
Okay.
Okay. And then you train your model. And then you train it over and over and over again. If you see that the accuracy is not getting any higher, then it means that the complexity is not um being effectively captured by the number of neurons you have. So you might either want to increase the number of layers, hidden layers, or increase the number of neurons in the layers. Okay. All right. So, because as I mentioned, the hidden layer captures the complexity of the data. Okay. So then we have the output layer. Output layer. Then I mentioned that the connection between the neurons is what? The lines represent what? Who remembers?
The
Yeah, the
weights,
weight.
right?
Please,
The
you wait.
weight. Yeah, the
Yeah,
weight.
the weight.
The weight. Now, every input neuron is connected to every hidden neuron in the sorry in the feed forward neural network. Okay, so that's what we have here. Um, so let's just define our data now. Let's say that our whole data set we have two examples of houses. So there's a house one which has two rooms, has a size of 120 meters square, and then has one floor. This is our first data point. Then our second data point has 10 rooms. Size of the house is maybe 500, and then the number of floors is 3. Okay, so let's call this one here. Let's call them data points. Data points. Okay. Now with um the neuron the neurons, yeah, the neurons, the weights between them actually are numbers. So these lines here represent numbers. And as I said, the number is what is the level of influence that this particular input is having on this. So the weight values will just be some numbers. So what I'll do is, usually when you are training the model, as I mentioned, the training process is the process of setting the weight values. So basically, you are going to be changing those values over the training process. So you start with random values. You can start with maybe, it's not usually good to start with all zeros, but you can start with all ones or some randomly selected numbers. I'm going to start with all ones. So I'm going to assume that every weight here has the value of 1. All the weights here, all the weights here. Okay. So in the training process, what happens is that you initialize the weights biases, select your activation function, and then you give in your data points in the input layer. When you give it in the input layer, it would calculate what um, the value should be up to the output layer. Okay, what do I mean? So the first calculation that will happen will be this. Okay, before I go there, sorry, you guys, sorry. This is the this is the data point, right? So this is the number of rooms, size of house, number of floors, and then it's supposed to correspond to the price of the house. Okay, so let me add the last value here being the price of the house. So for this one, it's a smaller house. Let's say it to be worth um maybe 12,000 cedis. Okay, and let's say this one is worth 100,000. 100,000 cities. 100,000. Okay. So in this one here, the last point here is your label. So it's actually the price of the house. Okay. So in the training process, what's going to happen is that the first three, which represent the data, would go into the input layer like this, and then you will calculate forward what should be in this neuron, and then consequently what should be the price based on the weights. So the first pass we would have Okay, I can do equation. The first part would be 2 times 1 plus 120 times 1 plus 1 times 1. And then, oh, sorry. And then you enclose all of that. And you add your bias. Let's say the bias is also 1. You add your bias. And then you enclose all of that into your activation function. The common activation function that's used is sigmoid. You can also use ReLU, but let's just go with sigmoid. So, oh, you're not able to see what's happening. Is it that the writing is too small, or I don't know how to zoom it from here, but I think you should be able to try and zoom from your side. Okay. So let's do this small mathematics for me. We have 2 times 1 plus 120 plus 1 plus 1. So 2 plus 120 is 122 plus 1, 123 plus 1, 124. Okay, so the sigmoid of 124. Sigmoid is, I think, 1 over 1 plus e to the power negative x. So it means that the output will be 1 over 1 plus e to the power negative 124, which should give us, does anyone have a calculator to calculate this for us?
It says it's 1 approximated, 0.99999, so like 1.
Okay, so it's approximately 1. So let's do, so approximately 1. Okay, so this is the output. So basically, the movement from this first neuron to this one gave us 1. So this neuron now has a value of 1 as its input, and it will be passed to the output layer. But it will have to be multiplied by some weight first. Now we already assume that all the weights are 1. So it means that this one here is 1. So moving from this neuron to this one is a similar calculation. It will be this weight times this value here. So 1 times 1 is 1, which means the outputs from here um would be okay. Well, this is not just from here, but it's from all these neurons. Hello. Okay, so what this basically means is that the model with the current weight has predicted the price to be 1. However, the actual price is 12,000. Right. So you can see that there's a very vast distance between what the initial configuration of the model predicted the price to be and what the actual value is. So there's something called backpropagation. Backpropagation involves going back to change or to tweak the weights based on the level of distance or discrepancy between the prediction of the model and the actual expected value. Okay. So that's
Haruna, can you
basically how it
please
works.
mute?
Do you understand?
Can we get Aruna to mute? The distraction is a lot.
All right. So sorry about that. Um, are we okay? This is not a technical. It's not supposed to be this debate. I guess you want to understand. Um, this is what we mean by the training process. So the training process is basically taking the data points through using mathematics kind of like this. Yeah, I'm tired. Taking it through with some kind of mathematics like this, comparing the final answer at the output to the expected answer, and then based on the discrepancy. So the larger the distance from the distance of the prediction from the expected value, the the greater the change would be to the weights based on that. Okay. And so that's how the training process works. So what I showed you, this calculation here is moving from inputs, right? What? It's called a forward pass. Okay. So this calculation is a forward pass. And then that process of identifying how close the prediction is to the actual value is is done by the loss function. And then using the the discrepancy to modify the weights backwards is called back propagation. Okay, let's go back to the slides. We have like 20 minutes more now. Um, any question? Is the information too much? I feel like the information might be too much. Um, it's a lot. There's a lot we have to cover in a small period of time.
And how well do we need to know this for the certification? Is it do we need to know everything or?
You don't need to know it that deep, actually. That's why I don't have all the math in the slides. And I try to make the slides really focus on what you have you seen the course outline? I mean the let me see. This is it. This is the exam. Have you seen the exam guide? The things that you need to know are in here. It's a multiple choice, blah blah. Um, I mean, I think you should have it, but if you don't, I can share it. But basically, the math is not going to be part of it, so don't be too worried about that. It's just for you to understand the basic ideas that are in here.
Please, can you share it on our page on WhatsApp for us?
Sure, I'll do that.
Thank you.
Oh, I see some comments here. Yeah, sigma is not the same as log. It's not. Um, yes, backpropagation is to reduce the error. That's exactly what it is for. It's to reduce the error. Spot on. Yeah, I'll share it with you guys. Don't worry. Um, it's online though. I got it from online, so you can literally just Google it. You find it. AWS AI Practitioner Exam Guide. But I also share it. Um, so as I told you, we already went ahead of the slides. So the engine is how the neural network actually gets smarter. Now, what's the mathematical calculation we did, multiplying and adding values, is what we call the forward pass. So the data flows from the left, the input layer, to the right, the hidden layers, all the way to the output layer in the network. And each layer is transforming the data slightly until the output layer, sorry, produces a prediction. Okay, so from input layer to layer one, then hidden layer one, hidden layer two, then output. This is for this particular example that we have here. Okay. Um, and then you can imagine it as a message being sent through a chain of translators, right? Each translator changes. the message slightly. But by the end, the original message has become a meaningful answer. Okay. So, I mean, when you go to the site, you see there are a few tips, like things here, exam related things here, based on the exam guide. So, the forward pass is called inference when it's used on new data after training. Okay. So we know what training is. Training is the forward pass plus weight updates. What weight updates are the back propagation. Okay. Repeated thousands of times. And then we have inference. Inference is just so inference is after you've created a model, and you're actually using it to make predictions. The the process of making predictions with a trained model is the inference. Okay. And the batch is the number of training data that you are training a model with at a particular time. Usually you don't just do one, you do a couple of them together. So you call that a batch. Um, and then real time is okay, so there's batch inference, which is making doing several predictions at the same time, or real time inference, doing them one at a time. Okay. OPL, okay. These are stuff that we have just discussed in detail. That's why I'm not spending too much time on it. Loss function. So the loss function, remember I told you that after we went to the forward pass, we got a 1. So the price was basically 1 CD. Meanwhile, the expected price was 12,000 CDs. And I told you that that level of discrepancy would determine how the weights would change. So the larger the discrepancy, the more the weights would change. The loss function is the thing that quantifies the level of discrepancy. Okay. So if you think about it, just um how do I say intuitively, you would calculate the loss, like intuitively calculate the loss by just subtracting the price you got from the output from um the expected value. So that would be 1 minus 12,000, right? Um, but this may work for certain cases and not for other cases. And that's the reason for the loss function. Okay. So the loss function is what is going to help you quantify that um, mistake or discrepancy. So it helps us know what is the level of um, or how wrong are we? Okay, what's the level of the mistake? So after a prediction, we compare it to the true answer. The loss function measures the gap. How wrong was the prediction? So if the model predicted, for example, 320,000 euros and the actual price was 280,000 euros, then the loss is 40,000. Um, in this case, you're using a square error loss, so that's 40,000 squared. Okay. Common loss functions, we have the MSE, which is mean square error, and then cost entropy. So MSE is usually used for regression problems, which is what we have here. And then cost entropy is usually used for classification problems. So usually when you're training a model, it always starts with a very large loss. And if you are doing the right thing, the loss should be reducing as you train it until it gets to a minimum value. Now, when it gets to a minimum value, uh, then your model is at the best position it can be, unless you make some further adjustments, whether to the number of layers or to the technique you are using. Okay. And what happens if you go further when it has reached its minimum is that the loss has to increase again, which is the indicator that um your model um might be overfitting. Okay, which we'll talk about later. So loss is like your GPS recalculating after a wrong turn. It doesn't yell at you. It just quietly measures how far off you are and plans the correction. Okay. Any question at this point? I know that this is very technical, so I'm very conscious of the fact that I might have lost you.
At one point, you were going to use the playground to explain, but I think you got distracted or something like that.
Oh, sorry. Where is it? Um, I wanted you to explain um the architecture. Thank you for reminding me. Okay. So this is the input layer here. And then these are the hidden layers. This is the output. So you can see it here. There's the data, the features, the hidden layers. Can you see? Hidden layers. Yeah, and then the output is here. So we can increase the number of hidden layers. For each hidden layer, we can tweak the number um of neurons in it. Okay. And then for the outputs, yeah, these are all hidden layers. Over here, there are no neurons showing, but it's rather showing the way the decisions are being made. Okay, so we can set an activation. Let's set sigmoid. Oh, sigmoid is not very good. And then so the plot you are seeing here is the loss function. Okay, let's stop training now. I want to restart it. Uh-huh. So initially, this is how the data looks like, right? Um, it's more of a classification kind of problem. Let me pick another data. Let's pick this one. So for this one, it's very clear that the model should learn it to be, somewhere divided here so that everything around here is orange, everything around here is blue. Okay. So at the beginning, the training loss is 0.5, test loss is 0.48. Okay. Now when I click play, training is going to start. And when training starts, the loss should reduce. Okay. So you see over here, loss has reduced and come all the way to 0. Okay. So this is just a visual um explanation of the way the training process is working, really. Or let's say, um, yeah, basically. Let's try and complete what we have. Any questions? Okay. So backpropagation, as I mentioned earlier, is the process of learning from mistakes. After computing the loss, the network works backward, asking each weight, how much did you contribute to this error? Okay, so um the for the backpropagation process, it starts with calculation of the error. So the loss function tells us how wrong the prediction was. Then the blame is distributed backwards. So using calculus, the chain rule, each weight gets a blame score called a gradient. Okay. So um we get the error. Then we look at, as I mentioned, the weight is the level of importance that's assigned. So if we get a really bad score and we go back and see that, oh, this neuron had a very large weight assigned to it, it means that that neuron was very loud in in making the claim that this is it and it wasn't. So you would tweak the weight to either reduce. So if the neuron had a large weight and the answer was very wrong, then it means that the weight should reduce, right? If the loss was high, then the weight should reduce because um it contributed more in giving the wrong answer. If the the loss is low, um then it should increase, right? So there's that. So then it basically takes the blame backwards, and then the weights are updated based on that. Usually it's a negative relationship. So the larger the loss, the lower the weights should go if they're high. Um, and the higher they should go if they are low. The weight values are what the training is all about. So the training is setting the weight values. Um, you and I don't determine the weight. They would be determined based on, well, the kind of loss function you use, but generally just your data. And the role of the hidden layers is to capture the complexity or the pattern in the data. Okay. So generally, we will be picking weights which are causing our loss to reduce. Okay. The most common method that is used for updating the weights is called gradient descent. Okay, you don't need to know too much about it, but just to know that it's a method for updating the weights by optimizing such that the loss reduces um or the loss reaches its minimum. Okay. Now overfitting, underfitting, and the Goldilocks zone. Did you come across these terms, overfitting and underfitting, in the previous session?
Yes, we did. We came across those ones, I think, under machine learning. Yeah,
Okay.
we came across underfit and overfit.
So the concepts are the same here, they haven't changed. So overfitting is when you train your model so much that it kind of memorizes patterns in the data without understanding. So when you show it new data, it performs badly on it. Kind of like chewing and pouring Pascal, but in the exam something different comes, right? So if you overfit, it means you just chewed the Pascal without understanding. So if new questions come, not be able to answer. In the Goldilocks zone, even while you were solving the Pascal, you were trying to understand. So when the new questions came, you were able to still repurpose your understanding to answer them correctly. And then underfitting is you didn't learn at all. You didn't even try Pascal. You just slept. So you didn't have enough knowledge to, or maybe you saw but you didn't solve enough. So you didn't have enough knowledge to answer. Um, then the next thing is to actually write some code. However, it's 5 minutes to time, and I don't think if we start, we'll finish. So we'll do that in the catch-up session, which I think I scheduled for Tuesday. I need to double check that, but I think we'll probably communicate that in the group. Um, in the group. But are there any questions? Any thoughts as we end the session? Was it too theoretical? Did you understand? Was it a sharp distance from or a sharp deviation from what you did in the previous phase? Why should the weight be increased if the loss is low? So generally um there's a negative relationship, or let me not say negative relationship, but you want to optimize the weights such that they minimize the loss. Okay. So basically, if um your loss is high, you want to modify the weight such that the loss will move um down. Okay. So why should the weight be increased if the loss is low? I mean, it depends. It depends on if the loss is low, should the weight be increased? The weight will just move in the direction that will minimize the loss. Whether what time I'm tired. The weight will just be moved in that direction that will minimize the loss. Whether it is increase, whether it means increasing the weight or it means reducing the weight. Whatever would cause the loss to reduce. Okay, I hope that answers your question. Any other question? Oh, Bennett answered it. Yeah, Bennett, spot on. Yeah. So the weight is managed to ensure losses minimized. Exactly. Yes, the bias also contributes to backpropagation. Um, yeah, it does. So the weight and the biases, we can think of them as they are quite they come together kind of. Okay. So wherever there are weights, there are also biases there. And they also contribute to the backpropagation. Yeah. Okay. Is that all? Are we all okay? What type of learning model does it is supervised. What we're looking at now is supervised because we have labels. The labels help us calculate the loss. So this is supervised. Oh, and this kind of neural network is called a feed-forward neural network. Feed-forward means that every neuron is connected to every other neuron. Um, so yeah. So and they all move in one direction as well. So these are all examples of feed-forward neural networks. Okay. As we go on, we'll meet other kinds of neural networks. Okay, we'll meet recurrent neural networks. This is an example of a recurrent neural network. So for the feed forward, you see that everything is just going in one direction. The recurrent, some of the weights are pointing backwards, some of them are looping into the same neuron, things like that. Okay. All right, it's 9 o'clock. If there's no other question, I think we'll end it here for today. Thank you for joining and for participating, and have a good weekend and week ahead.
All right. Thank you so much. We meet again.
Yeah. Oh, someone asked what I did. I did mathematics in the university, and I am doing AI. I did AI. I did mathematical sciences in masters, data-centric engineering, and then I'm doing a PhD in AI currently. All right. See you guys.